We're moving from different parts of the universe, and I'm now going to invite Fedor Vodolazskiy, who's got his doctorate in engineering sciences. He's based at the Ural Federal University in Ekaterinburg in Russia, so he's one of the ones who's traveled some of the most distance. We have a wonderful contingent from Russia and Ukraine, and very grateful to have them here. So Fedor is the first one we're going to hear from. He's doing research on material science, particularly in titanium, and he's going to talk to us about the correlation between material science and the Vedic system of sounds. Fedor.
Let me introduce myself. I'm associate professor in Ural Federal University, and the main topic of my research is material science and crystallography of titanium-based alloys. Also, I study Vedas, and during working on my main studies, I found some interesting correlation between crystallography and the Vedic system of sounds, and now I want to share this result with you. Before I start, I have some problems with English speaking. Sorry. If I will have difficulties during speaking, I will ask my colleague Adi Usmanov to help me. Adi, where are you? Let's go. Dr. Hammerhoff said yesterday there is about wave nature of quantum particles. So many scientists agree that there are only vibration on the subatomic level. Imagine that structural units of materials world have wave nature, and this interrelation is obvious. But do the interrelation exist on the atomic level? And the answer is yes. There is a traditional crystallography approach using 14 types of Bravais lattice. These types describes atomic positions of in the space. For example, in metals there are three main lattices, two of them cubics, third hexagonal, and they are ordinary have 2, 3, 4, and 6 fold of symmetry. What does it mean? The two-fold of symmetry means that after rotation on the 180 degrees, the atomic moves on to the same position. And for example, for the three-fold of symmetry, the angle is 120, and so on. Cubic has four-fold of symmetry, and hexagonal has 6-fold of symmetry. But this approach has some difficulties with describing lattices with five-fold of symmetry. They called missing solutions. But examples of such materials exist. The most popular example of them you can see on the screen, fullerenes. How we can fill the third space? The problem is how we can fill the third space without voice using such elements. And the answer is you must use another approach. Five-fold symmetry is comparable with transition, but only in one direction, and this is a problem. You can share this lattice on this whole space. Another approach. Next slide, please. Okay. A few scientists all over the world solve this problem. In Russia, for example, there is 2 scientists who make research on this topic. One of them PhD in technical science, Kropotkin, and second Thales, a PhD in physics and mathematics. They're a good example of collaboration between them. And I take the facts that they used in his research and add some new interpretations. The problem, next slide. The problem was five-fold fond symmetry. The solution is to how we can. The solution is to increase the dimension. For example, how you can fill the plane with pentagons. You can see that there is a gap between pentagons. How to do this without gaps? The answer is next slide, please. The transition from two-dimensional space to three-dimensional allows us to remove the gaps between the pentagons. This figure is called dodecahedron. Next slide, please. Like the rotation of two-dimensional pentagons in three-dimensional space, the gap between the polyhedra can be eliminated by rotating the three-dimensional polyhedron in a four-dimensional space. And the question, how to organize and describe four-dimensional space, and using the mathematics of complex numbers. Next slide, please. We cannot see four-dimensional space, but we can see the section of four-dimensional space but three-dimensional reality. For example, there is such figures called polytopes. This is a four-dimensional cube, his projection on the three-dimensional reality, and this is a four-dimensional sphere. And this is a projection of four-dimensional dodecahedron. Atoms are situated on the surface of these figures. Moreover, in the end of the 18th, the Japanese scientist Aizu proposed the concept of prototype or an prototype phase. The idea is there is a multidimensional forms that contains called prophase, that contains all possible variants of lattice for the particular material. And you may ask me, and where is the Vedic system of sounds? The Vedic system of sounds consists of 4 levels. The first level is para sounds, is a transcendental sounds. We can feel it anyway. Pashyanti is the sounds of our desires, connected with brain. Madhyama is the sound of the mind. And these 3 levels are out of our 3-dimensional reality. And vaikhari is a material sound. That's what we hear. One of the ideas is the high level of sounds control on low levels. For example, madhyama sounds organize the material sounds of vaikhari. And the transformation in the 3-dimensional space occurs through rotation of 4-dimensional objects and the change its section or projection by our 3-dimensional reality. Thus, there is a certain multi-dimensional lattice which contains possible variants of lattice and 3-dimensional reality. And I want to share with another example where we can see such interrelation. The comb. Bees began to build the comb from different parts of the hive. Where they finish, there is no any gaps in the center. A very, very accurate work. How it possible? As we know, they don't use any instruments. The possible interpretation is the existence of the multidimensional form of comb, and there is only one example. There are many more such examples in the nature, and this is a good opportunity to collaboration. And finally, its conclusion, there is a correlation between the crystallography and the Vedic system of sounds. The transformation in materials occurs through four-dimensional space, which is analog of the sounds of madhyama level. So, thank you. Question? Yeah. Too complicated, I think.
But very interesting, because it actually ties in with some of the aspects that I think Brenda and Peter, Stuart were talking about this morning. And perhaps, oops, yeah, sorry, I should. And I think it illustrates the way that information, which is ultimately what sound is, it's a vibration containing information, has the opportunity to interact with physical systems. So it may be something to tie your research with some of the other work that is going on with the other physicists.
Maybe
but thank you very much.
Okay, my question is for Dr. Vodolazskiy. I gleaned from your conclusion that through observation, 4D observation basically, that madhyama sound or mind sound has the capacity to cause matter to transform or change. I was under the impression that vaikhari sound, or like material sound, can also have that effect. So I was asking if you could maybe clarify or differentiate the madhyama and vaikhari in regards to its effect on matter.
As I understood the question is the difference between two levels, vaikhari and madhyama level, yeah? And vaikhari, what we hear, it's a rough level of sounds. It's a material world, 3D material world. But madhyama's level of sounds is a computational world, a level of our mind. It's what we are thinking. It's a level of ideas. It's they can be described through mathematics, through computational science, and for example, I show you an example of mathematics with complex numbers. They can describe four-dimensional space that we cannot imagine. Using our geometry, we can imagine only 3D space. We cannot imagine four-dimensional space. And this is the difference. I hope I answer your question.
If not, let us continue that privately.